Okay, guys, so this is the delta learning rule, which is there in the syllabus for you. Generally, this data learning rule, also known as gradient descent rule. In gradient descent, what we mean by a gradient descent is that we have error function, right? And this is for learning. So in this error function, we have to calculate a slope, right? And once we calculate a slope at a given point of time, we take a direction in the negative, we take a negative direction of that slope with some defined step size. For an example, right now I'm standing on this blue point, so I calculate the gradient in x and y direction. So these blue directions are showing a negative direction of the gradient. The resultant vector is this. So this is a negative resultant direction which is shown by black. You take a walk in this direction. Again, you calculate a gradient, negative gradient. That's why it is known as gradient descent. Descent means you're descending in the descending, or you are walking in the opposite of the gradient direction. Gradient is nothing but a slope of error function. So you will go till your gradient is converged to a zero, right? At the moment when you are standing somewhere where you cannot feel any slope, right? It means you are at the very plain, very horizontal side, and there is no elevation or slope at that moment. The gradient will be zero, and there you will stop. This is the criteria for gradient descent. This is another visualization. So we have a function which is x square plus 2y square. So the moment you start initially, you see that you are getting a bigger gradient, and when you take a direction, negative direction of that gradient, again calculate a gradient, and if you keep on doing this, finally you will converge to a point where gradient is zero, and you have to stop it, right? So this is another visualization. When you start this is a x square plus y square function. You start somewhere. You always, because this function is having a unique minimum, so it doesn't matter from where you ever start. You always converge to a unique point here. So there are different variant of gradient descent. One is known as coordinate descent. It means you always walk parallel to the axis. So this is one of the variant. You don't have to learn this, but just I have included just for the sake of understanding. Okay, so and then there are a lot of literature available for learning neural networks like SGD, stochastic gradient descent, momentum, NAG, ADA grad, ADA delta, RMS prop. So what in this slide we are trying to show here is that though there are a lot of variants, some variant converges faster than the other variants, right? For example, in this case, this black one, RMS prop, is like converging faster than any other one to the unique minimum. But if you see like this blue one, which is ADA grad, is getting into the closest proximity at first, right? So there are a lot of variant available on this gradient descent, which people adapt for their own purpose. And mostly if you are in the deep learning field or neural network field, so you find that people, most of the time people end up in using this ADA grad, right? Okay, so there is a choice of learning rate. So though visually we have understood like what is this gradient, once we calculated a gradient, we get the direction like where we need to walk, right? Where we need to walk. So for example, if you're standing here and you calculate a gradient, you see that the gradient is in this direction, which is a positive direction. You take a walk in the negative direction. But when I say that you have to take a walk, like you need to decide what is the step size. If you take this much step, then you come directly here. If you take this step, then you come here. So it depends. So it is a hyperparameter in this learning, and this is a choice of learning. So if you stand somewhere, you calculate a gradient of a function, and you decided, once you have a gradient, you decided that you need to walk against this direction. But then the first thing that you should, that's the thing that comes to your head, is like what is the step size I should choose, right? The bigger step size have some pros and cons, and similarly for smaller size, right? For an example, if you're standing here and you take a bigger step, you come here directly, and again you calculate a gradient, which we actually calculated decent gradient. Again you take a bigger walk, you just skipping a minima at this point, right? Because you are taking a very bigger steps here. If you are taking a very small steps, right, just converging to the unique minima will take forever, right, if it is with you are taking a very smaller steps. So this is a hyperparameter. What generally people do in neural network learning, they just at the initial stage of training of neural network, this is like a warm up stage. They take a bigger steps, and at the time when they find it out that they are near to the some minimum global local minimum, they just fine tune this step to a smaller size, right? This is an adaptive step size. Okay, so this is all intuitively I have shown you. I will take one small example in terms of a linear regression, because this is a very old technique that you might have gone through in most of your semesters, and if not, like, you don't need to worry about that, right? I will just explain a bit. So what linear regression says, that you have like 2 points here, right? Just a minute. Oops. Okay, so let's say you have 2 points here. So um, these are the 2 points. You need to fit a function here. When I say linear function, so the only thing that comes to my head is a line. So there could be multiple lines. I start with some random line, which could be this. Then I see what is the error of that, right? What is the error means, for this given x, what is my y? This is my y, right? For x1, this is my y1, and for x2, this is my y2, right? This is my y2. So if I just come start with some random line, the moment I say I start with a random line, it means I started with some random parameters. It means I just have taken randomly some slope and intercept. So I have not taken care like what is my intercept and slope of this line, but I have just chosen randomly, and then I thought of like, if this could be my line, what is the error that is given by my data set? So this is the error that is there for my data set, right? I calculate this error, and I will try to minimize this error. In linear regression, how I will calculate the error? So my line equation is this, right? So this is W transpose X. So this is my line equation, right? This is my line equation. And what is my label? What is my target value? This is y1, right? So for my x1, this is my intercept and slope, right, which is fixed. So I fix this intercept and slope in this parameter w, and I just take a dot product with my x. I will get some prediction. This is my prediction, right? This is my prediction p1, which is for x1. So I take my prediction p1. I calculate, so this prediction is right. So this prediction is nothing but W transpose X1. And what is my actual label? My actual label is Y1. So I will see like what is the difference between my prediction and an error. So this I can get a negative value and a positive value for this expression, right? I can get a negative value and a positive value for this expression. If you take then there will be a problem, right? For some expression you can get a negative value, and for some expression you get a positive value. So just to avoid that thing, you just take a square of this function. Right now everything will be whether it is a positive entity or a negative entity, it convert to a positive entity. And the good part is you will calculate this error for every point, right? So it means this is a point for x1, and the error for x2 will be W transpose x2 minus y2, and you take a square of this error as well, and the total error will be, you just sum them up, right? So this is the total error. So if this is my error function, now the good part is this error function is convex function. If you just plot it, you will see that it is like a kind of a parabola, right? Now if you take a gradient of this, it means you take a because this is a function, error function, and the only thing that you can change here is W, right, which is intercept and slope. So now it means this is a function, and I can change my parameters W over here. So if this is a parameter, right, then there will be some error. If this is my W, intercept and slope, there will be some error. If this is my W, right, this will be my error. So let's say I have taken some random line which give me this error. I will calculate the gradient at that point, and I will take a walk, right? I will come here. Now this is my new line. I will calculate again an error. I take a walk. This is my new line, and I keep on doing this, and finally I will converge to a line which will give me the minimum error. The moment I try to fine tune further, I will see that my error will start growing. Hence, now what we need to do is, the thing is that I have told you is that I have calculated an error function. If I take a gradient of this error function, right? Gradient means slope. This is what I will get it, right? This is what I will get it. And this gradient, if you see, if you want to update your W, so your old W was this, right? This was your old W. You are taking a gradient, which is this, right? You are taking, for now I'm just noting it with gradient E, right? E of W. If this is your gradient EW, right? You take a walk in a negative direction, right? You take a walk of a gradient in a negative direction, and what it will give you, this will give you new W, right? And you keep on updating this rule. Okay, so I just so this will be my rule of updation for this gradient descent. Okay, okay, guys. If you have any question, we will set up some discussion period for some day, and there we will get some clarification if you have any. Thank you very much.